this is working. Okay, like I said, today's class is going to be about metal semiconductor junctions and then photodiodes. So we cover those two topics today, then we'll be done with the diode chapter. Both of these topics are pretty important in the sense that metal semiconductor junctions turn out they're very important when we talk about our next module, when we talk about MOSFETs. So it's going to be a critical concept. A more practical thing is anytime you want to actually connect a semiconductor to a circuit, you obviously have to connect a wire to it. So at some point, there's going to be a metal semiconductor interface. And if you don't understand that interface well, you could end up having behavior that you're not expecting. For example, the two things that we're going to talk about today are Schottky barrier diodes and ohmic contacts. There's two types of components that originate when you touch a metal to a semiconductor. In the case of a Schottky barrier diode, that connection might actually have diode-like properties itself. And that might be unexpected. But it turns out that if your metal semiconductor work functions are such that you may end up having diode-like properties. If you just want to make a nice ohmic contact to a junction, meaning you just want to be able to connect electrically into the semiconductor, then the type of junction that you would like is an ohmic contact. So a low resistance junction that forms an electrical contact between the wire and the semiconductor. And the symbols for an ohmic contact is just a resistor. You want that resistance to be as low as possible if you want to make a good contact to a semiconductor. And then this is the symbol for a Schottky barrier diode. Okay. This is when your metal semiconductor junction forms something that has more diode-like properties and can only conduct current in one direction. So that would be bad if you're trying to make a nice contact. So we're going to talk about where these two types of contacts originate from. And the best thing we can do is just go back to the basic concepts. And this is one basic concept I'd like to touch on again from before. This is what the work function is. Turns out this work function is an important property of both metals and semiconductors. So if this is going back to Einstein's experiment. As you all might recall, Einstein discovered something called the photoelectric effect, and that was the thing that he won the Nobel Prize on. So what the photoelectric effect was, you have a piece of metal. Okay, and that piece of metal is in vacuum. Okay, you bombard that metal with light of varying energy. Let's say you start off with low energy light. How is energy related to wavelength?
Higher energy equals shorter wavelength.
Higher energy is shorter wavelength, right? So let's say you're doing an experiment where you're starting off at large wavelengths, low energy, and you're just gradually ramping up the energy. So that's what they're doing here. You're bombarding the metal with light, and you keep on increasing the energy. And then over on the right side, which is not shown in this diagram, is you have an electron detector. Okay, there's various types of electron detectors. We're not going to get into how those things work. But basically, the electron detector would detect when an electron is ejected from the metal. So the experiment was you're turning up the energy of the light, and at some point, you start to see electrons being given off by the electrons like popping out of the metal. Okay, and furthermore, if you continue to increase the energy of the light, the energy of the electron also increases. Okay, now the energy of the electron. Of course, you can measure the velocity. If you have the velocity of the electron, that will it's kinetic energy. So higher energy electrons travel at faster velocity. But the thing that we're focused on here is the work function. Okay, when you put very low amounts of energy, if you put low energy light and you shoot the metal with it, you will not eject electrons because the electron needs to absorb a certain amount of energy in order to be ejected from the lattice. You have to have that minimum amount of energy. So that energy required for the electron to escape from a solid material into vacuum is called the work function, and they denote it by Q times phi in the energy band diagrams. Okay, and when we talk about the work function of metals, it's phi sub m, and then when we talk about semiconductors, it's phi sub s. Okay, so what I want you to picture in your head again is the work function is the energy required. You imagine our energy band diagrams. The energy required to completely release an electron into out of the material. Okay, so I'll talk more about this here. So if you provide enough energy to an electron, it'll jump into an energy state which represents the electron, the energy of an electron freed into vacuum. So that's let's look at this, the energy band diagram for metal. So this is back to chapter 3. If you recall, in a metal, so this is energy on the y-axis, a metal might have various energy bands, but one of the key things about a metal is that the Fermi level occurs within the band, in the middle of the band. So what does that tell us about the band? What?
Always conducting.
It's always conducting because
There's no band gap.
there's no band gap.
Empty states.
Yes, that's right. There's remember, below the Fermi level, there's below the Fermi level, most of the states are full, right? So below the Fermi level, most of the states below here are full, and then above the Fermi level, most of the states are empty, right? So this single band has both a lot of carriers and also a lot of empty states. That's what you need to conduct electricity. All right. So in a metal, you can say that there's no band gap here at all, right? In this particular example, we're just showing a single band, and this band becomes very conductive because the Fermi level happens to be located right in the middle of it. So what we're talking about with the work function, the work function is an energy state way up here, okay? And when an electron attains this level of energy, it is ejected from the metal. That's the photoelectric effect. So in order for that to happen, the metal has to absorb this amount of energy, Q times phi m. Q you already know, right? And then phi m is the work function. The work function phi m is typically given in volts, and if you multiply volts by Q, you get a unit of energy in electron volts. Okay, so this is what a metal looks like. In a semiconductor, so the metal work function Q phi m here. Now in a semiconductor, remember that you have the conduction band and you have the valence band. Then within there you have a Fermi level. Okay, most of the electrons are down here below the Fermi level, but there are some electrons. Could be some electrons near the conduction band up here as well. The conduction band, we denote that here. The bottom edge of the conduction band, we denote that EC. The top edge of the valence band, we denote EV. I don't have that here. But the work function is defined similarly for the metal. The work function is defined as if you have this E0, okay? E0 represents an electron that is freed from the lattice. It's completely out of the semiconductor material. So let me remind everyone what these different energy states means. If an electron is in the valence band, well, what does an electron in the valence band represent? Physically.
In the orbits?
It's in the covalent bonds, correct. Yeah, in the orbits, in the covalent bonds. So an electron that's participating in the covalent bonds is part of the valence band. If an electron happens to be in the conduction band, what does that represent?
It's forming about the lattice.
Yes, it's loosely bound to the lattice. It's one of those free electrons, mobile electrons. But it's loosely bound to the lattice. It's not completely free. Okay, so an electron will be able to move through the solid material. If you go even higher in energy, E0 represents an energy when the electron has enough energy to escape from the solid material completely. So it's like it's completely outside the material. It can be ejected from the material. So the photoelectric effect could also apply to semiconductors. And there's a semiconductor work function, Q phi s, that you see here. And that Q phi s is the work function for semiconductors. Okay. Now with the metal, there's just this work function. In semiconductors, there's something called the work function. And there's also an additional thing here called electron affinity. So that's the distance between EC and E0. Okay.
Is that a literal distance?
Oh yeah, these are literal distances. Yeah. So the work function for the metal is the distance from the Fermi level to the E0, the vacuum energy level. E0 is called the vacuum energy level. So the distance in the energy band diagram from here to here is Q phi m. And in the case of a semiconductor, again, the distance between the Fermi level and E0 is Q phi s. And the distance between the conduction band and E0 is Q times X. And X is called the electron affinity. Okay, the reason why semiconductors have this factor, this electron affinity, is because remember that the Fermi level can change depending on how you dope the semiconductor, right? So if you want to have a true constant, then you use the electron affinity. The distance between E0 and EC doesn't change in silicon. EF could change based on the doping, right? That's a key thing. Any questions on the work function? Okay. All right, so now we're going to talk about the energy band model for the N-type Schottky barrier.
Oh, I do have a question.
Yeah, let's go back.
So, is there any situation where you're going to eject electrons from the valence band by hitting it with?
Yeah, hypothetically, if you were to supply enough energy, if you supplied enough energy to go from EV all the way up to E0, you could eject an electron from the valence band, sure.
So my question though is, so could you still have electrons in the conduction band theoretically that just like fall back down to that valence band, if that makes sense, in that situation?
Well, if you, okay, let's look at it this way. If you were to supply an energy greater than the electron affinity, then you'd start removing electrons from here, and those electrons would go into the free energy level, right?
Right.
If you were to supply more energy beyond that, let's say you supplied enough energy to go from the valence band all the way up to E0. These electrons have shorter distance to go, right? So those electrons would still probably be the first to go, right?
But,
and then these ones would also
theoretically
go.
Possible to still have electrons in the conduction band and eject electrons from the valence band.
Is it possible to? That's a good question. I think in order to answer that question, you need to know like what the probabilities are. Like the Fermi-Dirac statistics are all about probabilities, right? So when you blast a material with high energy light, there's some probability that some electron will absorb that energy and go into the high energy state, right? It's not 100% probability. It's not a 0% probability. So in my mind, I would imagine that based on Fermi-Dirac statistics, that there should be some small probability that there could still be an electron in the conduction band if there are electrons going from the valence band.
Just curious.
Yeah, it's a good question. So this is an N-type Schottky barrier. This is one of the 4 types of possibilities that we're going to talk about. Okay, the 4 possibilities originate from what type of metal semiconductor junction is it? Meaning, like, do you have an N-type or P-type metal, or do you have an N-type or P-type semiconductor with the metal? That's the first question. So there's 2 possibilities there: N-type or P-type. The second question is the metal work function greater than or less than the semiconductor work function? So it turns out that depending on whether you have an N-type or P-type semiconductor and whether the metal and semiconductor work functions are greater than or less than one another, you end up having 4 possible devices. And the first of the 4 devices that we're going to talk about is the N-type Schottky barrier. Okay, so this particular example happens when you have a metal and an N-type semiconductor, and the metal work function is greater than the semiconductor work function, as you can see here. Phi m is greater than phi s. And this particular device ends up behaving like a one-sided diode. One-sided diodes we talked about earlier, a P plus N junction or an N plus P junction, where one side is much more heavily doped than the other. And, one side contributes most of the depletion width, the lighter dope side does. So it behaves very similarly to a one-sided diode. So imagine that you have the metal and the N-type semiconductor here. We're going to draw the energy band diagram for it. So again, just think about this as an exercise in drawing energy band diagrams. You have a certain set of rules that hopefully you should know better by now than you did a month or two ago. So the first thing you want to do here is draw the semiconductor on the right side. You're already familiar with how to do that because you know how to draw the band diagram for a doped semiconductor. So let's just say that we had an N-type semiconductor like this. So you have a Fermi level here that's above EI and below EC as it should be. And then you have your valence band down here. Okay? So this part should be pretty straightforward. The position of the Fermi level, as you know, it depends on the doping. And the higher you dope it, the Fermi level goes higher. The lower you dope it, the Fermi level goes towards EI. And then in a P-type semiconductor, eventually it goes towards EV. So, but now the difference is you have a metal on the other side. So, okay, let's draw in this E0 as well. So we didn't add this to the band diagrams before. We're going to add them now because that E0 is important for figuring out how this material interacts with the metal. Okay. So the next part is you draw the metal. Okay, and the key thing about drawing the metal is you line up the Fermi level and then you add the E0 on there. So why do we line up the Fermi level? Let's look at this. So what we're going to do here is we're just going to extend the Fermi level out this way. Why do we do that? What's the rule with the Fermi level in energy band diagrams?
It should be horizontal.
It should be horizontal. Under which conditions? Yep. Equilibrium. You got it. Yeah, you got it. Good. At equilibrium, the Fermi level is a flat horizontal line. When you apply voltage to the system, the Fermi levels are going to be different, right? Whichever side has a positive voltage has a lower Fermi level. Remember that. Equilibrium, though, there's no voltage being applied, so the Fermi level, they're all going to be at the same energy. Okay, so flat horizontal line. So we use this to align the band diagram of the metal. All right, so the band diagram of the metal we draw like this. We don't even bother drawing the band, the band that has the Fermi level in the middle of it. We just draw EF. So the band diagram for a metal is super simple. It's just EF and E0. That's it. So the distance between EF and E0 is the metal work function, which will be given to you. You know, the metal, this is one of the characteristics of a certain type of metal, is that it has a certain work function associated with it. It's a material property. All right, now, so we have E0 up here, and then we also have E0 down here. The difference between this diagram and the PN junction, with the PN junction, remember we had EC, EV, EI on both sides of the diagram, right? Do you remember how we connected them together? We connected those together. So in this case, the metal doesn't have EC and EV. It only has E0. So it turns out that the E0s have to be continuous. Just like with the PN junction, the EC and the EV had to be continuous. All right, so when you connect these two, this is what it ends up looking like. You start here, and then you actually draw a line like this connecting up to the top, and it looks like this. Okay, so the line goes up like this, and so the two E0s connect with one another. All right, now you might be wondering, why doesn't it look like, why isn't it curvy on both ends? If you remember in the PN junction, there was curvature on this side of the diagram as well. But in the metal semiconductor junction, there's only curvature on this side of the diagram. This is because of the way that metal forms an interface with the semiconductor. Does anyone remember what the slope of this line tells you?
Electric field?
The slope of the line tells you the electric field, right? Good. If you have a sloped line here like this, what else might it tell you? If you think back to the PN junctions, what does this sloped region represent?
Depletion.
It represents the depletion region, correct. So it turns out you end up getting a depletion region on this side of the junction as well, in this type of material as well. Okay, so you have this sloped region here. That means you have electric field, and that means you have a depletion region. So again, let me just back up here and show you again how to do this. You draw the band diagram of the N-type semiconductor. You line up the Fermi levels. Okay, so you extend the Fermi level out this way, and then you draw the E0 for the metal based on what the work function is. And then the last step is that you connect E0 together. And after you connect E0 together, you also do the same thing for EI and EV. Because E0, EC, EI, and EV, they all have to run parallel to each other. The distance between those energy states doesn't change. That's determined by the band structure of the material. It cannot change. So if one of them bends up like this, the other ones have to bend up as well. Okay, so that's what's happening here. Now we can think about how do we interpret this. Just like before, we think about an N-type semiconductor, and we say, well, if I want to look at what's happening in the N-type semiconductor, I'm going to first think about what's happening with the majority carriers. Okay, the majority carriers, there's a lot of electrons there, so I'm curious what the electrons are doing. So imagine that there's a lot of electrons here, just like before. And the electrons, the electrons would like to be able to go back and forth like this. If the electrons were to move, if they were to try to move in this direction towards the metal, they would encounter this barrier here like this. This is called the barrier height. Okay, so very similar to a diode, that once equilibrium is established, the electrons no longer can diffuse over to the metal side. There's a subtle point about this that I think it's worth talking about, because it may help you understand some other aspects here too. Let's see here. I'll just draw this out.
Are there states between E0 and the conduction?
Are there states between the E0 and conduction?
For the between the metal and the...
There could be higher energy states. There could be higher energy bands. But if there's no possibility of electrons being in there, we usually we don't even bother drawing them, because there's nothing interesting happening there. But yeah, there is. It certainly is possible. You could have higher energy states. So if we think about what's happening here, let's say we have the EF of the metal here. And then this is Q phi S. So the subtle point that I was saying is that initially, if you were able to actually do this in practice, which is you can't physically do this, but like if you were to take a metal and a semiconductor and just they're apart initially, and then you just bring them together, the moment, if you were able to somehow measure this, the moment that the metal and semiconductor came into contact with each other, that moment the E0s would actually be lined up. Okay? Let me draw I'm going to draw the Fermi level for the semiconductor. So this is EF for the semiconductor. And since it's an N-type semiconductor, this is going to be EC, and this is going to be EV. Okay? So the instant the two materials are brought into contact with each other, this is what the band diagram looks like. All right. Now, you imagine that you have a bunch of electrons up here, because this is an N-type semiconductor. And the electrons are like, well, where can I go? Electrons can move horizontally, right? Horizontal movement is okay. And going to lower energies is also okay, right? Electrons don't like to go to higher energies. They can move, so that means in the band diagram, they can move horizontally and then they can move down. So the electrons would see that here, that they have, notice that the Fermi level the Fermi levels are different. So initially when the two materials are brought into contact, this has a higher Fermi level than this side does. All right, so what that means is you have a bunch of electrons up here and a bunch of energy states down here. So the electrons will just want to flow down like this. Okay, as the electrons are flowing down, you're depleting electrons from this right side. If you deplete electrons, what happens to the Fermi level?
Goes down.
Fermi level goes down. All right, so the Fermi level is actually, as you deplete the electrons, the Fermi level is going to come down until it matches the Fermi level on the metal. Okay, so that's that subtle but important point is that there's a rapid transient that establishes equilibrium. This happens almost instantaneously. Yeah.
Does the Fermi level of the metal go up as well?
Does the Fermi level of the metal go up? Well, the Fermi levels are always discussed in relation to one another, right? When we do notice that when we do our Fermi level calculations, it's always EF minus EC, EF minus EI, EI minus EV. We're always doing these calculations relative to other energies.
So does E0 minus EF get smaller when you bring a highly doped?
That's basically the question.
Does
the distance between E0 and EF get smaller at the point of connection after you connect?
So is it almost like the excess electrons in that semiconductor is doping?
The electrons initially when you bring the two materials in contact with each other. Yeah, the electrons see a lower energy state in the metal, so they all go into the metal. But as the electrons are depleting from the metal, the Fermi level, that means the Fermi level is coming down. When the Fermi level comes down, the EC also comes down, the EO also comes down. Everything comes down. I don't know if that was clear or not.
So no, that's completely clear.
So all of them are actually coming down.
So the question is by adding the electrons from the semiconductor to the metal, is the opposite happening to the metal?
Meaning the Fermi level is going up? I usually think about this in relation to each other. In relation to each other, the Fermi level on the right side of the diagram is coming down.
Yeah, that's absolutely clear. Yeah.
So
if you take it not in relation to each other, but in terms of absolute value, what's going on?
I suppose you could think about that the Fermi level in the metal goes up. But if you just think about it in relation to one another, yeah, one's coming up, the other one's coming down, but they're being matched up. Yeah. I don't think that's a great answer to your question, but I hope it still gives you the idea. So where were we here? Yeah, so that the equilibrium that's quickly established at the right side of the band diagram came down. Okay, and now the Fermi levels are lined up, but you've formed, because E0 have to be connected to each other, you can't have E0 here and then E0 here and just have a discontinuous thing. There has to be a continuous region in the middle. Okay, so that's where this barrier forms. And once that barrier is formed, once equilibrium is established, that barrier height prevents additional electrons from dumping over into the metal. Okay, at that point, equilibrium is established. What does that equilibrium mean? Well, because you have this slope in the band diagram, that means you have an electric field. What does the electric field tell you about built-in potential?
There is some.
There is a built-in potential, just like there is with the diode. Correct. What's the difference between this and the diode? You can see a lot of similarities. What's the difference?
For my level, what that,
well,
their level did not change even here. Right?
Yeah, that's a similarity actually. In both cases, the Fermi level at equilibrium is a flat line.
Instead of this sharp.
That's a key difference, right? Yeah. In the PN junction, you have a curvature here and a curvature here. Here you have an abrupt.
I And the depletion region just happened in the N-type semiconductor, nothing happened in the metal.
That's right. That's right. You have a depletion in a PN junction. You have a depletion region on both sides of the junction. Here, you only have a depletion region on one, which is why the diagram looks like this. And then one final point I would add is that in the band diagram, we also have the holes that we think about. In a PN junction, we have the holes that also have a barrier here. In this case, it turns out that the holes actually don't have a barrier. The holes can actually go freely back and forth like this. Because if you think about this band diagram, below the valence band, as you know, in an N-type semiconductor, there are mainly electrons up here, but there's some very few holes. Holes like to go up the slope. So if there were a hole down here below EV, the hole could go up this way. So the hole could transport up this way.
So if that were p-type, there would be almost no holes and a lot of electrons freely moving?
We'll get to the p-type
Okay.
in just a second. That's a good question. So this is behaving very much like a one-sided junction diode. All right, so you have your built-in potential here, QV0, and then you also have this thing which is different from a diode. You have this thing called a barrier height. The barrier height is the distance between the height of this barrier compared to the Fermi level on the metal side. Okay, and just from this diagram, you can quickly see that the barrier height is equal to V0 plus EC minus EF. Just from this diagram, you can see that. Right? So V0 is equal to phi m minus phi s. Phi b is equal to phi m minus electron affinity. Let's go over that for a minute. This is just an important point that I want you to note about the band diagram. This is phi m, and then this is phi s. And this distance here, this distance is the amount of bending in the band diagram, and this is equal to QV0. All right, so if we look at phi m, this distance here, this arrow here, and then this is phi s. So this first statement is saying that the built-in potential is equal to phi m minus phi s. So this QV0 is equal to this large distance minus the smaller distance. Okay, and this QV0 is the same as this QV0 here. All right, and the barrier height is equal to the work function of the metal minus the electron affinity. So the electron affinity, again, is the distance between EC and E0. And that's something that would be given to you on a test. And if you happen to know the built-in potential, then you can also know the built-in potential. And if you know the doping, then you know this distance. That's another way to calculate the barrier height. All right, so here's a physical model of the Schottky barrier. Imagine that you have a metal here, and then you have this N-type semiconductor on this side. So what happens is that, as I mentioned before, the electrons diffuse to the surface of the metal and accumulate there. Remember when I was saying here, this initially, when you put the two materials together, the electrons in the semiconductor actually have higher energy than the electrons in the metal, so they would actually move over to lower energy states here. So there's a very small transient that happens where the electrons are depositing themselves on the metal surface like this. Okay? And so this charge accumulates on the surface here. These black circles are electrons that were deposited on the surface of the metal by the N-type semiconductor. Okay. Now, one important rule about metals, which you may or may not remember from electromagnetics, or you might remember it from electromagnetics. You might remember it from, if you've ever visited the science center, like a science experiment where you touch that ball and your hair goes up. Have you ever seen? Yeah, it's electrostatic. That's right. The electrostatics is what makes your hair stand up. Why was I thinking of that? Oh yeah, the reason I was thinking of that is because that ball, like you touch this metal ball that's highly charged and then your hair stands up, that ball has the reason it's able to transfer the charge from the ball to your hand is because all the charges are on the surface of the ball. There's a fundamental rule with metals that if you charge a metal, the charges are always on the surface of the metal. There are no charges inside the metal. You know, if a metal acquires a positive or negative charge, all the charges are distributed along the surface of the metal such that the electric field in the middle is zero. Okay, so
Professor, that kind of hits on one of the questions I had earlier.
Yeah.
Is that because of the charge accumulation on the outer envelope? Is that why that QX doesn't change? So when an electron is emitted from a material, it always gets shot from the surface, never from the middle.
Oh yeah, absolutely, yeah. If the metal happens to be charged, then there's going to be a bunch of electrons right on the surface. So it's easier to eject a metal from the surface than it is from like inside the material. Yeah, good question. So what's happening here is that the electrons from the semiconductor, again, they deposited themselves on the surface of the metal. So you form this negative charge here, just on the surface of the metal. There's no depletion region within the metal. No depletion region. This is all just negative charge that accumulates on the surface. But in the semiconductor, within the semiconductor, a depletion region forms like this. Okay? Why does a depletion region form? Well, all these electrons deposited themselves on the surface here. Those electrons came from the semiconductor. All right, and so when the electrons left, what you're left behind with is those negatively charged ions, which is those red circles, and that's an immobile positive charge. All right, so there's similarities here, and that's in the sense that you have a surface negative charge here, and then you have this positive charge, and that forms essentially a single-sided depletion region with an electric field, just like there is in a p-n junction. Which direction is the electric field pointed? Just from this diagram.
Right to left.
Right to left, correct. That is correct. It's pointed from right to left because electric field points from positive charge to negative charge. All right, so it's pointing from the red circles to the black ones. All right. So this has a certain depletion length associated with it, just like before. But this depletion length is basically the entire width of the depletion region. There's no depletion region on this other side, so the entire width of the depletion region is just the depletion width on the semiconductor side of the junction. Okay, and you can imagine the same type of physical model happens in the case of a p-type Schottky barrier, which we'll get to in a second. Any questions so far? All right. So this is what a Schottky barrier looks like in the forward and reverse bias. We looked at the band diagrams in equilibrium. This is the equilibrium band diagram, and then these are the band diagrams in forward and reverse bias. So same as before with the diode, the key concepts of diode are kind of coming over here in the Schottky barrier as well. Forward bias increases diffusion, it reduces the barrier height and increases diffusion. And reverse bias does the opposite. It increases the barrier height and it decreases diffusion. It increases the electric field. All right, so this is what the band diagram looks like in the forward bias. Remember in a p-n junction diode, how there was this barrier here, and when you put forward bias on the diode, that barrier height became smaller. Same thing is happening here. All right, this QV0 becomes QV0 minus V. So I'm jumping around here, but at equilibrium, this barrier formed on this side is equal to, has an energy difference of Q times V0. This gets reduced by however much positive potential you put on the diode. All right, so this becomes Q times V0 minus V. All right. So you are applying a potential to the left side, so to the metal side here, and applying a positive side to the metal causes this Fermi level to be lower than the Fermi level on this side. So it brings, whatever side you apply the positive voltage to, it brings the other side of the Fermi diagram, the Fermi level on the other side higher. So that reduces the barrier height. That increases the diffusion of electrons to the metal side. And so your current goes way up. In reverse bias, you do the opposite. By applying a reverse bias, you're bringing the right side of the band diagram lower. And so this barrier, this energy potential barrier here, it increases by an amount equal to whatever reverse potential you apply. So this is going to limit diffusion. And as you can also see here, because the slope, now you have a steeper slope. A steeper slope means a larger electric field. Okay. I sort of asked this question already, but I'll ask it again. How is this different from a diode? Let's see if there's anything else we can come up with. How this might be different than a diode. Well, one thing I can mention is, in a diode, you put the diode into forward bias. You increase the diffusion of electrons, right? Same as you are here. You also increase the diffusion of holes on the other side of the diagram, right? You're increasing diffusion both ways. In this case, you're only increasing the diffusion of the electrons, or whatever's on the semiconductor side. Okay, so that's another example of a difference. The IV curve for a Schottky barrier looks very much like a diode. You have a small reverse saturation current here in the reverse bias, and then once you go into forward bias, the current increases exponentially. So the equation is the same, I0 e to the QV over KT minus 1. That's the equation for the current of a Schottky barrier diode. The difference is how you calculate I0. If you recall, for a diode, the I0 depends on the diffusion lengths and the doping on the two sides of the junction, on the N side and the P side of the junction. In this case, you only have a semiconductor on one side of the junction. So the I0 actually turns out to be an equation that's related to the barrier height. So I didn't give you an equation here where you can directly calculate I0. So I would typically give you I0 if it were on an exam. But know that this I0 is exponentially, it's related to the exponential of the barrier height, inverse exponential of the barrier height. So if the barrier height becomes smaller, then the I0 becomes larger. Okay. All right. Good. Any questions about this so far? So I think the things you'll be expected to know, just be able to do some basic straightforward calculations on this, and of course to be able to draw the band diagram and explain some of the physics associated with the Schottky barrier. That's what I'm looking for here. Let's talk about a p-type Schottky barrier real quick. If you want to make a p-type Schottky barrier, you have to choose a metal and a p-type material where the semiconductor work function is greater than the metal work function. Notice that this is different than the n-type material. In the n-type material, you wanted your semiconductor work function to be less than the metal. For the p-type Schottky barrier, you want the semiconductor work function to be greater than the metal. So I'm not going to go through the whole steps of drawing the band diagram again. I'm just showing you a shorthand using a diagram that's in the book. So imagine initially when we bring the two materials together, the E0s are lined up. Okay, that's this blue line up here. So let me just label that E0. This is the vacuum level. Notice that the Fermi levels are not lined up with each other yet. Okay, so within a very, very short time, equilibrium is established. And how is equilibrium established? Well, notice that this time we have a p-type semiconductor. So in a p-type semiconductor, we have a lot of holes. So we can start by drawing the holes in the band diagram. All right, holes like to go up the slope, just like electrons like to go down the slope. Holes go up the slope because a hole moving to a higher energy means that an electron is moving to lower energy. So the holes would go this way. All right. So as the holes go over to the other side, that brings up the Fermi level on the right side of the diagram to a point where now the Fermi level is lined up. Okay. Since the holes have moved over, there's a depletion of holes on the right side of the junction, similar to the electrons. So you imagine what happened. You put the metal and the semiconductor together. The holes in the semiconductor moved over to the surface of the metal, and that's what's causing these positive charges. The holes moved over like that. But because the holes left, you're left with the depletion region. And the depletion region just consists of those negative immobile ions. And you can see this in the band diagram. The way that you can see it in the band diagram, I'll describe to you another thing that's a useful way of thinking about the band diagram. If you look at out here, the distance between EF and EV is small. What does that tell you about the hole concentration?
There's a lot in the valence band.
Yes. The closer EF is to EV, the more holes you have in the valence band, right? Now look at the distance here. Larger distance. Okay, so if there's a larger distance, what does that mean? There's less holes, right? So that corresponds with our physical model, that the holes have left this region. They've diffused over to the other side. And so this area here, the depletion region, one of the reasons why it's called a depletion region is because that region is depleted of the majority carrier. It's depleted of holes. The same thing applies with the n-type Schottky barrier as well. So larger distance means fewer holes. And then vice versa here. So similar to an n-type Schottky barrier, there's a barrier. A barrier that forms here, and it's equal to Q phi s minus phi m, and that is your built-in potential, the Schottky barrier. So this one has operational characteristics similar to an N plus P diode. The n-type Schottky barrier has characteristics similar to a P plus N diode. All right, now let's talk about ohmic junctions. So ohmic junctions are metal semiconductor junctions that are designed to operate like a resistor rather than a diode. So this is what the IV characteristic for a diode looks like. It's exponential, and then it saturates on the negative side. This is the IV characteristic for a resistor. It's a linear element. So if you double the voltage, you double the current. If you cut the voltage in half, you cut the current in half. So the IV characteristic for an ohmic junction is going to look like a straight line. Notice that I've actually drawn two lines here because I want to ask you the question, which one is a better ohmic junction and why?
In the middle.
In the middle, which one are you referring to?
Flatter.
Are you referring to this line?
No, the other one.
You're referring to this line.
I agree with that.
This one is the better one.
Yeah.
Okay. Why do you think that?
This is the slope. This is 1 over R.
Yeah, you got that. That part's correct. So
need
if you remember, V equals IR. So if we put this in Y equals MX plus B form, this is I. I is on the Y-axis. So let's put it this way: I equals 1 over R times V. So this is the slope. 1 over R is the slope. Okay. In an ohmic junction, do we want a large or small resistance?
Small.
We want a small resistance. Why do we want a small resistance in an ohmic junction?
Less heat dissipation.
Less heat dissipation, right? Right. We don't want to add resistances into the system. If we're just trying to make a contact into something, we just want it to be a low resistance contact, right? So then, which one of these two lines has a lower resistance?
Flatter line, because it.
It's
actually,
1 over R.
it's one. The slope is 1 over r. So this has a lower slope, right? This has a smaller slope. So this actually has the higher resistance. This one has a larger slope. And so it has a smaller resistance. So this is the one that will make the better ohmic contact. So if we choose our metal and semiconductor work functions appropriately, we can actually get an ohmic junction. So let's see, if we choose the work functions opposite for the Schottky type, so we choose phi m is less than phi s for an n-type metal semiconductor junction. Phi s is less than phi m for the p-type metal semiconductor junction. That's one way we can get the ohmic junction. The second way is by using what's called the tunneling type junction. We'll get to that in a second. But let's look at the n-type ohmic junction first. All right. Again, there's two diagrams. This is before equilibrium, and then this one is after. Okay, and I'll mention again that equilibrium is established very, very, very quickly. So this is what the band diagram looks like initially. Remember that E0, the E0s are lined up. Okay, the difference here is that phi m is less than phi s. All right, so phi m is less than phi s. Watch what happens. So how can we think about this? This is an n-type ohmic junction. So you have electrons here. The difference is now you also have electrons. You have electrons below the Fermi level on the metal side. Now those electrons are actually at a higher energy. So those are the ones that end up going down here. So as that happens, the Fermi level on the right side relative to the left side goes up. And eventually the Fermi levels form a straight line like this. But now what's interesting is that the E0 on the right side ends up being higher than the E0 on the left side. And so all the bands actually bend downwards instead of upwards. All right, so look at this. This is quite interesting. Now we have a situation, we have an n-type semiconductor. So, n-type semiconductor. So imagine a bunch of electrons up here. Okay, and the electrons, notice that there's no barrier here this time. Okay, when phi m was less than phi s, now you have a situation where you have an n-type semiconductor but no barrier. Instead of like this, which is where there was with an n-type Schottky barrier, now there's no barrier like that. So let's erase this. So now what happens is that the electrons can move freely into the metal because there's no barrier. And the second point is this ends up usually being quite small. The energy difference here ends up being quite small. So the movement can actually happen both ways, assuming that barrier is the barrier in the opposite direction is fairly small. Okay, so this is the kind of ohmic contact you want. You want a contact where the carriers can flow freely in one direction as well as the other direction. Okay. So what we want to do, of course, is we would like to in some cases, if we want an ohmic junction, we have to design it this way. Okay.
Is the electric field flipped as well, or is there still a depletion region? It looks like it.
It's drawn here as there's a depletion region, but that depletion region is actually negligible. There's current can flow freely between both sides.
So there's pretty much no electric field at the interface?
Very, very little. You can look at the band diagram here. Hold on, I have to reload. Give it a second. Okay. Notice that there's a slope in the electric field, right? Or the slope in the energy band diagram. If there's a slope, that means there's an electric field. The difference is that this slope is over a small region. And so a lot of times, like if you have an ohmic contact that's designed properly, you can neglect it. It doesn't take very much voltage to overcome that small barrier difference.
And that's what you would want, right?
That's what you would want.
Okay.
Exactly. Yeah, imagine like if you had a diode and the contact that you made into your semiconductor was behaving like a diode and only allowed current flow in one direction. That would be pretty rough, right? So in cases where you want to make a metal semiconductor contact, you want to design it to be an ohmic junction. And so how do we do it? We just chose a metal with a work function that's smaller than the semiconductor work function for an N-type. For a P-type, it's the opposite. So with the P-type ohmic junction, phi S is less than phi M. I'll let you all do this at home as an exercise because I think that doing it on your own is helpful. And I'll let you figure out why this is an ohmic junction. The final thing I'd like to talk about here is the tunneling type ohmic contacts. So this is what a Schottky barrier looks like. This is an N-type Schottky barrier. And you saw this, you already saw this a few slides earlier. So this barrier height prevented the electrons from diffusing over to that side. However, there's an effect called tunneling that happens if the band diagram looks like this, meaning like there's a slope there, but so that the width of that barrier is very, very thin. Then it turns out that the electron can actually punch through the barrier instead of having to go over and across it. So the only way an electron could make it over to this side is actually to go above the barrier like this. And it's not likely to do that. A very low probability of that happening. But when the barrier becomes very thin, then the electron can actually go right through the barrier. Okay, it turns out that this effect is called tunneling. There's a whole theory on it that we could talk about with the modern physics chapter that I went over in module 2, but there's just not enough time to really cover that. What I do want you to understand with tunneling, we talked about it a little bit with Zener diodes as well, is that the smaller, this is where an electron goes from a higher to a lower energy state, but it goes through a region where there's an absence of energy states. So in this little region here, there's an absence of energy states, but because that region is so small, the electron can go right through it. Okay, this is sometimes called punch-through tunnels. They say the electron punches through the barrier, and the reason why it's called that is you can think that if you have a concrete wall, a thick concrete wall versus something that is thin as paper, it's obviously easier to punch through like paper, right? That's why they refer to it as punch through. So they're trying to build up an intuition there. But it turns out that the probability of tunneling is exponentially related to the width of this region here. So the width of this region here. So the smaller that width becomes, the probability of tunneling goes up exponentially. So one way of creating a very thin barrier is just to make the semiconductor doping very large. So if you have a metal in contact with an N+ material, you will end up getting that tunneling, like a barrier that has a really narrow width, and that can allow conduction through this tunneling effect. Right, so at low doping, it would behave as a Schottky diode, but at high doping, it would behave as just an ohmic contact because of this tunneling effect. Does that make sense?
So,
yeah.
Don't the electrons line up at the surface of the metal though?
That's on the other side of the junction. So there are a bunch of electrons here, right on the metal surface. But the point is that the electrons, they can tunnel through this barrier, so that allows the movement of electrons back and forth.
clear in this.
You're processing. Yeah, that's fine. You can
I'm
think
thinking
about it.
long term, eventually you're not going to reach the point that you can tunnel anymore, right?
No, because the semiconductor is doped high, high doping means you have a very, very narrow depletion region. That's what this is telling you. When you have a very small width here, that region where there's a slope in the band diagram, so this is the depletion region in a moderately doped semiconductor. In a highly doped semiconductor, the depletion region is very narrow.
So
that has to do with the doping. That's not going to change over time.
So then do the electrons diffuse through the metal, and then that basically opens up more states to continue doing this?
They tunnel through the depletion region and they go into the metal.
Right.
Does that make sense?
That does, but I'm saying, so I thought that there was a situation where you had a metal, and the metal had all these electrons at the surface, more or less, right?
Yeah,
So then
that's
those
true.
more or less those states have to open up over time in order to continue tunneling through, correct?
Yeah, like an electron can replace one of those states, and then the electron at the edge goes into the metal. Yeah, that's a good question.
There's a few things.
So this is what an actual diode looks like. This is a P-type silicon wafer with a patterned N-type region. As I said before, like if you take a P-type semiconductor and an N-type semiconductor and just like slap the two together, you won't get a good diode because the two materials can't be atomically flat, right? There's going to be little air gaps between them. So you're going to have a silicon-air interface instead of a silicon-silicon interface. If you take like a P-type and an N-type material and you just push them together, right? They're not both atomically flat. You can't have a perfect contact between them. So what's done instead is you start with the P-type wafer, which is at the bottom here like this. Why is my... yeah, once it's in ink mode, I'll keep it. Yeah, once it's in ink mode, then it doesn't let me use my mouse anymore. That's why I have to wait and restart it. Yeah, it's kind of annoying, but anyway. You start off with the P-type wafer, so you start off with this stuff down here, and then you diffuse. You use a process called diffusion, where you, here, I'll just draw it here on the right. Let's say you start off with a P-type wafer here like this, and then you want to diffuse an N-type region into it. So what you're going to do is you're going to create something called a mask. And that mask is just, you're basically covering up a portion of the wafer. And typical materials that are used are something like silicon dioxide, which can grow naturally on the surface of the silicon, or you can use, actually silicon nitride is sometimes also used. So I'm not going to bother with the details of that. Just assume that there is some kind of masking material, and that masking material is patterned, meaning like in some places the masking material has been removed. Now you put this whole thing in your diffusion furnace, all right? And in the diffusion furnace, you pump down to vacuum, you increase the temperature, and then you flow in a gas, let's say a column 5, a gas that has column 5 elements in it. And so let's say phosphorus. So phosphorus is all you're flowing phosphorus everywhere. Here, some of that phosphorus gets onto the surface, and those phosphorus atoms go here. I'm sorry, it's a little confusing. This is a P-type material, and this is a capital P standing for phosphorus. Some of those atoms actually get to the surface, and then they drive down into here like this. And wherever the phosphorus atoms go, you've selectively doped that material N-type, so you create an N-type material wherever you didn't have those mask regions. So you can actually pattern the N-type region within the P-type wafer. So you can actually do many steps of that. Let's say the first step, you decide to do a diffusion, and by putting it in the furnace for a long period of time, you can get a deep diffusion well. The first time, so you get an N-type region, and then you do another diffusion in a smaller region, and then you diffuse that with very, very high concentration of dopants, so you make it N+. Does that make sense? Oh, I see a confused look. So you can control how much you dope by controlling how long you keep it in this furnace.
Well,
the longer you keep it in the furnace, the further those gas molecules will diffuse into the material. You can also control the concentration of gas, and you can also control the temperature. So you have all those three variables. That allows you to actually control the junction depth here, and it also allows you to control the level of doping. So what you're looking at here is p-type silicon. By diffusion, you've created an n-type region here. And within there, you can do another diffusion step and create an n+ region, which is basically a very highly doped n-type material. And then here you can do a third diffusion step and create a highly doped p-type material just within this region. So by doing that, yeah.
Two things. This is on the like nanometer scale, right?
Yeah. Oh yeah, micrometer scale.
Okay.
Yeah.
Are the walls of the well always so, I'll call it perfectly straight?
There's a little bit of undercut because, wherever you mask this, if you mask it like this, there's actually a little bit of diffusion of the phosphorus atoms this way too. So there's a little bit of undercut. Okay. And so there's people in the semiconductor industry have mastered this. They have beaten it to death and more. Like they can control these things to like tens of nanometer precision, if not better than that. I mean, Intel's making transistors that are 10 nanometers wide. So they have extremely high levels of control of this stuff. And it's really, really crazy. Every process that Intel does, it costs them more than $1 billion to develop that process. And then they milk that process for many years. And then,
over very, very long periods of time, does this basically become useless though, due to diffusion?
If you were to put it in the diffusion furnace for an infinitely long period of time?
Basically, yeah.
Yeah, I mean, in principle, yeah, it could, if you kept it in there infinitely long time, then it would diffuse everywhere. But diffusion, the distance it diffuses goes as a square root of time. So it would take an insanely long time to get, the initial amount of diffusion happens quickly, but to get it much further than that takes really, really much longer. It goes as the square root of time. So there's a whole process of diffusion. There's a whole science behind that. There's entire classes dedicated towards microfabrication. I'm just touching a little bit on it right now. The main points I want to talk about here is notice that you have this P+ region here, and you put a metal on top of that. This makes your contact into the P portion of the diode. All right, so essentially what we're doing here is a diode looks like this, a P-type material and an N-type material, and you make an electric contact to it to connect it to your electrical circuit. All right, so what we're doing here is we made a diode in a planar fashion. And so in order to make a metal contact into the P-type material, what we first do is we create a P+ material here, and we also create an N+ material here. And the reason we do that is to make a tunneling type contact. If you make that, if your metal is connected to a highly doped semiconductor, then you'll always have an ohmic junction. You won't have to worry about Schottky barriers. You won't have to design the metal work function, choose the right metal so it has the work function that corresponds to an ohmic junction. You won't have to worry about that at all. If you just dope this with, if you dope this region a P+. Similarly with this thing here, where this N+ region is just to make an electrical contact into the N region. And where is the diode? Well, we often talk about, when we drew the theoretical diode, we said that this is the area of the diode. If you imagine that, if you imagine this as a three-dimensional kind of device where you have the P-type and N-type material together, the area of a diode is everywhere that P-type material intersects or is touching the N-type region. So in a diode, in a diode that's made like this, the area is here, on the bottom here like this, and here. The area is actually on all sides of that N well. So if you imagine this in 3 dimensions, how many sides are there?
6 total.
Yeah, well,
5.
It's 5. It's actually not 6 because the top one is, you got it. Yeah, so there's actually 5 sides. So in practice, when you're calculating the area of a diode, the engineer lays out what the structure is going to look like from the top. Your process engineer figures out how deep, what the junction depth is, and from that you can figure out the area of the diode. So this is a process that's used to make diodes. It's also the similar process is used to make solar cells. Okay.
Is the depletion width uniform around the entire interface, all 5 sides?
It should be. Yeah, it should be. So if the doping's the same and the voltage potentials are the same everywhere, then yeah, you form a depletion region on all 5 sides. So yeah, you got it. You got it.
And are we gonna use the same metal for both, like the N plus and the N plus?
Yeah. So if one of the reasons for using these tunneling type contacts is that you could use the same metal for both, without any concern of forming a Schottky barrier. Yeah, that's a really good question. That's one of the reasons why these tunneling type contacts are done. If the semiconductor fabrication facility can use a single metal for all the metallization, that makes their life a lot easier. Yeah. I'll leave this for you to do as an exercise for each combination. Choose whether the junction is ohmic or Schottky. Should be pretty straightforward from what we've done in the notes. And I want to spend the last 20 minutes on photodiodes. This is something that's not typically covered in the undergraduate class, but I think it's helpful to talk about it here because of the important role that photodiodes play in energy generation and then optical communication. So the 2 big applications, I mentioned this, I'll just go back to pull up the slide from one of the first lectures. Excuse me.
This is not in the Canvas, right?
Which
The
one?
Photodiode is not in Canvas now?
Oh yeah, I actually just added it this afternoon. I apologize. I usually like to try to get the notes up on Canvas beforehand, but I just didn't have time this time, so I'm just gonna go over it. I think I can cover it in the next 20 minutes. Oh boy, this might take a while. All right. Well, while we're waiting for that to download, I guess it did. Yeah, this was. This is the slide I showed on one of the first days of class, and this is a photovoltaic, right? This slide talks about the importance of photovoltaics. Like obviously, you all know that solar energy is a big part of the solution to fight climate change and to have renewable energy. And a couple of the key points that I like to always remind myself, is that on a bright sunny day you can get 1,000 watts per meter squared. That's a lot. A kilowatt per meter squared of area. So that's quite a bit of energy that can be produced if you're able to harvest that energy from the sun. And so these are some examples of photovoltaic panels that Google and Germany had done. You guys have heard of some of the Tesla solar panel roof tiles that are coming out, that have come down in the last few years. One of the things with solar panels, now that you have a little bit more idea of silicon and carrier generation, you can already see one of the things here is that the solar radiation, terrestrial radiation, means the solar energy that hits the surface of the Earth, not the stuff out in space, but the stuff that gets to the surface of the Earth. You notice that there's some dips in here. The reason why there's dips in there is because there's certain molecules in the atmosphere absorb some of the sunlight, so not all the solar radiation gets to the surface. It gets absorbed in the upper atmosphere. But you notice that there's a very wide spectrum, right? Can anyone tell me what is a portion that silicon can collect? And why? This will be a good lead-in into the discussion on photodiodes.
The right side?
Right side or the left side?
Silicon is transparent to infrared.
Yes, you remember that. Great. Why is it transparent to infrared?
Because it doesn't have enough energy to...
Yes,
the
exactly.
band gap.
Exactly. This is wavelength on the x-axis, right? So as we go to the right side of the diagram, it's lower energy light. In order to form a carrier in a semiconductor, you have to have enough energy to what? The energy has to be greater than what?
The energy, the band gap.
The band gap, exactly. So the band gap for silicon corresponds to something like, I believe like somewhere around like 1,000 nanometers or so. So things below here can be there's enough energy in the photons for the silicon to absorb it and then create an electron hole pair. The stuff out here, silicon is not going to be able to do that. What do you need to have out there in the larger regions? What kind of materials would you like to have out there compared to silicon? You have semiconductors, but
Bigger band gap semiconductors?
close, lower.
Smaller.
It's the opposite, yeah. Yeah, but you're right in the sense it has to do with the band gap, right? So out here, you actually want to use lower band gap semiconductors.
Germanium?
And germanium has a lower band gap, yeah. But a lot of times the gallium arsenide type materials are used. So I'll touch a little briefly on that. But this is the problem that we're addressing here. But what I'm going to talk about in the next like 15 minutes or so is the mechanisms of photodiodes. How do they work? Enough where you can actually do a simple problem on this. Okay, so the definition of a photodiode is this. You have a PN junction, right? And in the PN junction, you illuminate it with light. Okay, so in module 4, we talked about just an N-type semiconductor. You illuminate an N-type semiconductor with light, you generate, what happens? You generate electron hole pairs, right? But in that, if you just illuminate an N-type material, you can't actually generate power from that. Okay, because you generate, what happens when you illuminate a material in N-type? Let's just say, for example, an N-type material. You illuminate it uniformly. This is one of the questions on your exam.
We get carriers.
You get carriers,
And
right?
you turn the light off and they recombine.
Turn the light off, they recombine, right? Was there any current?
No.
If you uniformly illuminate a semiconductor, there's no current, right? So that's the thing. There's no current that can be generated just from a single type material. The key thing at the photodiode, now you have a PN junction. You have a P-type material and an N-type material together, and that turns out is what allows you to actually generate power when you hit it with light. And so this is a really cool phenomenon. So I draw a little diagram to help explain it. This is based on things that we already understand, fortunately. So understanding how solar cells work is actually within your purview already. So you imagine that you have a P-type material like this, and you have an N-type material like this. And I haven't drawn all the details in here. You already know what the carriers are doing. You know that there's a depletion region that forms, and I've split the depletion region up into two parts. Just as a quiz, what type of junction is this? Is this P plus N? P plus N. Why is it a P plus N junction?
The depletion
Depletion is
region.
shorter.
The depletion region on the P side is shorter than the N side. Great, perfect. All right. So the key factor in photodiodes or solar cells is that you have this built-in electric field that happens on its own. That's one of the really amazing things about semiconductors. You have the P and N type material together, you generate an electric field in the depletion region, and it turns out that electric field is key for generating current in a solar cell. So let's look at what happens. We illuminate this thing with light. Okay, we're going to generate electron hole pairs everywhere, right? You agree with that? But it's the electron hole pairs that occur near the depletion region that actually matter. So I'll show you why. So the first step, let's say we hit the material with light, okay, and let's say there's an electron hole pair that's formed here. You see the E and the H, right? They form in pairs. Now, what's going to happen to the E and what's going to happen to the H?
It's set in different ways.
Yeah, they can split.
Exactly. So this is the key part of why a photodiode works, or why a photodiode works, why a solar cell works. You generate a hole and electron in the depletion region, and they drift in separate directions because there's a strong electric field there. The hole goes in the same direction as the electric field. The electron goes in the opposite side of the electric field, right? Compare that to, let's say you generated an electron hole pair. Let's say you generated a hole here. And you generated an electron here. What's going to happen?
The hole will get pushed.
Well, let's say we just illuminate this region. We did something similar like this in Module 4. And you generate electron hole pairs. Do you remember how they diffuse out in both directions? If you have a specific region where you're generating a lot of carriers there, in that region you have a high excess carrier concentration, and outside it you have less excess carrier concentration. So diffusion happens from high to low concentration. So they just all, the holes and electrons, they just diffuse away from the illuminated source. But notice that the holes and electrons are both diffusing outwards away. Right? The key thing is that if you generate an electron hole pair in the depletion region, if you generate it in the depletion region, then the electrons and holes go in opposite directions, and that's really the magic of a solar cell. The hole goes in this direction, same direction as the electric field, and the electron goes in the opposite direction. So you can already realize why, like in solar cells, you want to maximize the P and the N interface. The area that we were just talking about, you want to maximize that area. Right? Just having a bunch of P-type material is not going to do it, and just having a large P and large N-type material that has a linear junction like this, that's not going to do it. You want to maximize the interfacial area between the P and the N materials. So another effect that happens, which actually helps us out generate even more current, is this. Let's say we generate an electron hole pair, but not just out in the neutral regions. It happens to be within one diffusion length of the depletion region. What's going to happen here?
More than half of the holes will drift to the P side?
Yeah, that's right. More than half, yeah. Yeah, that's close. The diffusion length is the average distance a carrier travels before it recombines. LP is the average distance a hole diffuses before it recombines. So if the hole is generated here, the hole is going to start diffusing, and if it happens to make it to the depletion region before it recombines, then it's just going to get swept across here like this. So let's say the hole manages to make it to the depletion region before it recombines. If it does, then it's going to end up drifting all the way through the depletion region and being collected on the other side, and boom, you get some current there. Similarly, on the other side, if you happen to generate an electron hole pair within one diffusion length of the one electron diffusion length on the P side, then an electron can diffuse over to the depletion region, and if it makes it to the depletion region before recombining, then it'll shoot over across onto the N side. So technically any electron hole pair that's generated within these three regions, the depletion region, and then one diffusion length on the N side and one diffusion length on the P side, those are all areas where you can end up generating carriers. So the equation for the current in a photodiode is quite simple. IOP, this stands for the optically generated current, is equal to Q times A times GOP. This is the optical carrier generation rate. And then LP plus LN plus W. All right. So what's going on here? What we're looking at is the total volume, right? We care about the total volume near the depletion region. So the volume of the depletion region itself is W, the width of the depletion region, times the area of the diode. Everyone agree with that? The volume of the depletion region is the width of the depletion region times the area, cross-sectional area. The volume of the region out here is LP times the area. So that's why you have this term in the parentheses. And then this side here is Ln times the area. All right. So what you're doing is you're taking the optical carrier generation rate, which is given in electron hole pairs per centimeter cubed per second, and you're multiplying that by the volume of these important regions. Okay, and that's basically how you generate a photocurrent. Now, any questions here?
How do you make that useful?
How do you make that useful?
How do you make that useful? Make this buildup of current useful.
Yeah, I'll talk about that. I'll talk about that in a second now. So, okay, we know that the current, we know that these carriers exist, and we know that they generate this current. And we'll talk about how to actually operate it. But before we get to that, let's show this. I'll get to your question in 2 slides, and then we'll get there today. The total photodiode current is now equal to the diode current, which we covered earlier in the module, right? This is the standard diode equation. Saturation current times e to the qv over kt minus 1. Standard diode equation, and the equation for the saturation current you already know. We covered that earlier in the module. But we have this new term now, okay? Notice that this is negative IOP, like the negative is because the current, the generated photocurrent, if you look at the direction, the holes are going from right to left, the electrons are going from left to right. The photocurrent is actually in the same direction as the electric field in the depletion region. So it's actually going from N to P. It's a reverse direction current. So it goes in the reverse bias direction. All right? So that's an interesting thing about photocurrent. It's a negative sign associated with it. And we just covered the equation for calculating the photocurrent. So if I give you a certain voltage, I give you a certain amount of carrier generation, you should be able to calculate the total photodiode current. What this actually looks like, the blue line that you see here is the diode equation that we covered 2 lectures ago. The equation looks like this. When you start adding photocurrent, when you start illuminating the diode, then the IV characteristic shifts downwards like this because of this negative IOP term. The more the light you put on the diode, the more this characteristic is going to move lower and lower. So this is actually the generated photocurrent. All right. So from a circuit standpoint, we're getting at how do you actually extract energy from this thing. There's 2 characteristics that we have to first be able to calculate: the open circuit voltage and then the short circuit current. These are both pretty straightforward to do. The open circuit voltage is defined as if you had a diode like this that wasn't connected to anything, and you shine light on the diode, what is the voltage that would be generated between the 2 terminals? And the way that you find that is simply by taking the total equation, the total current that we just saw on the previous slide, the regular diode current minus the optically generated one, and set that equal to 0. Okay, the reason we're setting that equal to 0 is because this is open circuited. Open circuited means that there can be no current, there can be no net current in the diode, so that I has to be equal to 0. Okay, so if you set that I equal to 0, then and you solve for V, the voltage here, then you get this open circuit voltage. And it's quite straightforward to derive the voltage here. You have this exponential. If you're solving for V, that's how you get this ln term here. So KT over Q ln of IOP over IS plus 1. IOP is the optically generated photocarriers, and IS is the saturation current for the diode. So this gives you the open circuit voltage. So if you had a solar cell and you shine a certain amount of light on it, this would tell you how much voltage you're going to get out of that thing. The second part is a short circuit current. This tells you what's the maximum current that this thing could deliver. The maximum current, of course, is when you short circuit it. That's when you get the maximum amount of current. And the way you derive that is by setting the voltage equal to 0. So in this example, we set the total current equal to 0. Here we take the same equation, we set the voltage equal to 0. So you have this Q0 up here, and then you get the short circuit current is equal to negative IS minus IOP. And note that it's negative sign, flows from N to P. All right.
What's IS?
I'm sorry?
What was IS again?
IS is the saturation current for the diode. So that, if you remember, we denoted that as IO before. You got it. Okay, perfect. Now this gets at your question, and I think this is right at the end of class here. Here's the typical regions of operation of a photodiode. If you guys don't mind just staying with me just like 3-4 minutes, we can finish this up. So the first quadrant, this is how we would connect a diode if we're just forward biasing the diode and not using it as a photodetector at all. We put a forward voltage on there, so the P side has a higher potential than the N side. You might have some resistor connected to the circuit, and then your current flows this way. So what you'll notice here, this is a key point, is that the junction voltage and the current are both positive. So by positive, I mean the P side has a positive voltage, the N side has a negative voltage, so it's forward biased. The junction voltage is positive, and the current flowing through there is also positive. This is what happens if we forward bias the diode. So that's what's called the first quadrant. We call these quadrants because this is the first quadrant here, where my mouse is. The second quadrant is here. We're going in a counterclockwise direction. Third quadrant is down here, and then the fourth quadrant is here. All right. So the third quadrant that we use is, this is where we reverse bias the diode. What happens if you reverse bias the diode? Do you get current out of it?
Yes.
You do, right? But very, very little, right? You just get that negative I0, the saturation current, the negative saturation current. If you reverse bias the diode, the diode typically only conducts current in the forward direction. You just get that very, very small reverse saturation current.
Unless you go over the breakdown voltage?
Unless you go over the breakdown voltage. Correct. So this is how we're biasing the diode. All right, so you put it in reverse bias like this. You might have some resistor in your circuit. Here's the thing. Now we've reverse biased the diode, and what does that do to the electric field in the junction?
Reverse the electric field.
Well, if you reverse bias the diode, it makes the electric field in the depletion region stronger. Remember the two effects. Forward bias, you're decreasing the barrier height, you're decreasing the electric field in the junction, you're enhancing diffusion. That's forward bias. Reverse bias, you're reducing diffusion, and because there's more of a slope in the band diagram, that means you have more electric field in your depletion region. If you have more electric field, you generate a carrier, and that electric field rapidly accelerates that carrier to the two sides of the junction.
More drift.
There's more rapid drift. The velocity is higher because the electric field is higher. And guess what that means? That actually means that your device is faster. If you put a large electric field on your diode, if you put a large electric field, a large reverse bias on the diode, and then you shine light on it, the thing will be able to respond very quickly to changes in light. Okay? Because of the electric field, the transit time of those carriers across the depletion region is very small. So that makes the diode very fast. So guess what this quadrant is great for?
High-speed electronics?
High-speed optics. High-speed photodetectors, where you're changing the light levels. Rapidly changing the light levels. Do you remember what the application of that was? Fiber optics. Fiber optics were sending information at gigabits per second by blinking lights on and off. Fiber optics relies on third quadrant operation of photodiodes. The fourth quadrant, now in this case what's unique about this is that the junction voltage and the current are opposite polarity. The junction voltage is positive, so you have a positive voltage on the P, negative side on the N, but the current is going from N to P. So that's in contrast to the first and third quadrant where the voltage and the current are actually in the same polarity. So the unique thing about the fourth quadrant is that the diode is supplying power to the external circuit, whereas in the first and third quadrant, the external circuit is supplying power to the diode. Okay, so in this case what's happening is that the diode, the PN junction, we haven't connected any voltage source to it. We're not powering the diode in any way whatsoever. But because of the carriers that are generated in the junction, now you have connected it to a circuit, and that causes current to flow through the circuit. This is the photovoltaic mode. Photovoltaic mode. So the fourth quadrant uses the photovoltaic mode, and it generates power when you shine light on the material. Okay, just two quick slides here that I want to show, just to show you some applications of this and some practical things. We obviously don't have much time to go into the details of it, but I just thought I might mention some of this to you. So photovoltaic cells, solar cells, are basically PN junctions with a few design tweaks to help maximize the conversion of light into power. So some examples of that thing you can see here. There's that there's an anti-reflective coating. You don't want the sunlight to bounce back from the solar cell. You want the solar cell to absorb it, so you put anti-reflective coatings on there. This is a semiconductor material that you see here in white. And on top, there's a thin layer of N-type material on the top. It's mostly P-type material, and then there's a thin layer of N on the top. And so there's a lot of interfacial area to generate those carriers. There's a lot of depletion region where you can generate those carriers. And then the final thing is you notice that this green thing on top that looks like metal fingers, that is done to reduce the series resistance of the diode. If you want to use a diode in a photovoltaic mode, you actually want to minimize the series resistance so that more of your power is delivered to the load. You don't want to have resistive losses in the diode. So that's one of the reasons why they put the metal fingers on there. And then one other thing here is that, as you know, we just talked about the fact that there's light of varying wavelength coming from the sun. So not all materials are going to capture all regions of the solar spectrum, right? So one of the tricks that people have done is that they create a multi-junction cell that looks something like this, which is basically a stack of semiconductor materials on top of each other. And you'll notice that these are all gallium arsenide-based materials with slightly different tweaks to it. Gallium arsenide is a good system because it allows you to tweak band gaps. So what you're looking at here is a multi-junction cell where there's a bunch of PN junctions, but each one of the PN junctions has different band gaps associated with it. So this one's ordered in decreasing band gap as you go from top to the bottom. By having materials with different band gap, you can capture more of the solar spectrum. So let's say the band gap here is too large. So the light passes through the band gap. It doesn't generate a carrier. The next one is the band gap's a little bit smaller. The next one is a little bit smaller. So eventually the sunlight's going to hit a material where the band gap's small enough for it to generate a photon, and there you go. You've generated current there. Unfortunately, these types of multi-junction cells are much more expensive. So the majority of photovoltaics out there right now is just basic silicon, basic PN diodes, which you learned in this class. All right. The last thing I'm going to talk about here is just this. We talked about the solar radiation spectrum already. You can see that we want to capture. I already talked about this. Is not really needed to go over this again. You just touch. I think this might find this interesting also. Also probably self-explanatory. This is from a slide that Professor Nasri has with his energy class that he shared with me. This is just showing the amount of solar energy that can be generated in the U.S. Different ranges. Obviously, here in the Southwest, where it's very sunny, you'll generate a lot of power. But 5.54 kilowatt hours per meter squared, which is pretty amazing. So these are some of the things that obviously like that we're working on right now. We're trying to deploy large-scale solar all over the country right now. All right. So to summarize up this chapter, we've talked about PN junctions, the equilibrium, forward and reverse bias. We talked about the physics, energy band diagrams, carrier behavior in each one of those cases. Then we talked about metal semiconductor junctions, which can behave either as a Schottky diode or an ohmic contact. And then we just touched at the end on photodiodes, which I think is probably one of the most interesting applications of diodes right now. Photodiodes enable the conversion of light into currents. And they're used for optical fiber communications in the high-speed mode in the third quadrant, and then in the photovoltaic mode in the fourth quadrant to create electrical power. So I hope that answered your question about how you extract power from the device. So any questions before we end today? Okay, thanks a lot for staying a little bit extra today. I really wanted to just finish up this module. We will have an online lecture on Wednesday and also next week. And we'll jump right into the MOSFETs. So I'm expecting that most of you will turn in your projects by 11:59 p.m. tonight, so I can give you some feedback on it. If any of you need any extra time for whatever reason, let me know. And if you need to turn it in by like early tomorrow, that's early to
For
noon
the
tomorrow.
citations, do they have to be super formal or just some basic information to get you to the source paper?
If you can put the citations in a format that's readable, like AMA or IEEE or something like something where I can see what the title of the paper is and where it's from, who wrote it.
Thank you.
In the final project, yes, I will expect that you have it in the IEEE format using a reference citation management.
Yeah, can we just kind of have like the names of papers in the outline, is that okay? Or-
Names, authors, journal, and year.
Okay.
Sorry.
I think I had a year on most of them. I'll add the title. And
I guess trade